Hello guys, welcome back to my channel. And in this video I would like to discuss uh, a useful property of the Laplace transform and naturally apply that to the problem of this video. So let's get started and I hope you learn something new today. So like always, even if this video is about discussing properties, I won't break custom because as always we have a problem integral that I call I, which is defined as the integral from 0 to infinity of 3 times e raised to negative 2x minus 2 times e raised to negative 3x minus 1 divided by 6x squared dx. Now if you're thinking that this question is pretty trivial, if you're wondering that this question is plenty trivial, then I mean you're not wrong, because you can see in which case that this can be solved using Leibniz rule or Feynman technique of integration, where you just select this parameterization. Say if I of t is equal to integral from 0 to infinity of 3 times e raised to negative 2x minus 2 times e raised to negative 3x minus 1 divided by 6x squared times e raised to negative tx squared dx, such that when you take the partial derivative with respect to t, or when you obtain I prime of t, this x square will come in the numerator and cancel out with the x squared in the denominator, so we get rid of that. But one cumbersome fact about using this technique is you have e raised to negative some constant times x squared, and then these e raised to negative single x terms, so you'll have to basically complete the square and you'll obtain something that's of the form of the Gaussian function basically. So e raised to negative some constant times x squared, and then you can apply properties of the Gaussian integral and stuff like that. But it's gonna get really cumbersome if you ask me. So I propose to use Laplace transforms, and not in the way that I did before, not in the way that we again need to parameterize this thing, say have a t, sneak in a t in the denominator and then take the Laplace transform of that, and then inverse Laplace transform of that, and then you let t equals 1 so that you get rid of the t factor. And I'm not going to do this. I'm not going to do this technique. I may have technique may have worked for the Gaussian integral and integrals of the past, but I'm really not going to apply the technique now. It's time to grow on. It's time to move on actually. So that's why I would like to introduce a new property, and I'll use a fresh page for it, don't worry, to discuss more about this new property of Laplace transforms and how you can apply them to calculate integrals. So this new property that we have roughly says that, say if we have an integral from 0 to infinity of a product of two functions, say f of x times g of x, an integration with respect to x, then you can write this as the integral from 0 to infinity of the Laplace transform of one of them, say f of x in this case, times the inverse Laplace transform of g of x dx. So this property may seem counterintuitive at the start. I mean, you have a regular integral and then you just introduce the Laplace transform, and then you multiply it with the inverse Laplace transform, and I mean you don't even invert the Laplace transform in the end and stuff. So it might seem pretty counterintuitive, but before actually trying to prove this, and don't worry, I'm going to prove this, I would like to just briefly tell you what the Laplace transform does. Say if you have a function of x, which is a function of x basically, it takes the value x and then gives an output, right? It takes in a number, it gives out another output number. But what a Laplace transform does, it is basically it takes in a function, say f of t, and spits out a separate function, a different function, which is now a function of s. So I mean, not only does it change the domain of the function, but also the function itself. So it's like a super function. That's what transforms do. They change functions of one type to functions of other type. That's what transforms do. Fourier transforms, Laplace transforms, Mellin transforms. There are many transforms. And if you want to define this, say the Laplace transform of a function f of t, in usual cases it's always a t, with respect to s, and I'll explain what this parameter is defined as integral from 0 to infinity of e raised to minus st times f of t dt. Now, with respect to s is basically the constant that we attach alongside the t in the power of e. So this original t is the starting domain of the function. So I call this the starting domain. So more like the input port, and S is the output port. I mean, you don't even need to have with respect to S. You can have with any constant. Say you have the Laplace transform of f of t with respect to, say, the natural log of a. So you have integral from 0 to infinity of e raised to minus natural log of a times t times f of t dt. So what this does is, in all the formulas of the Laplace transform, there's a whole table of them. Instead of s, you just replace s with the natural log of a. That's all you do. So again, notice that input t is also present in the power of e, and then the output domain is also present in the power of e. So remember this property, that e raised to output domain times input domain. This is really important going ahead with the proof. So I hope I'm making myself clear when I explain what Laplace transforms are. Let's get started now. Let me just clear up this mess. Now, if you look at the left hand side here, we are ending in a domain of x and we are starting with a domain of x. When I look at the Laplace transform on the right hand side, so it's basically saying that, remember the observation I showed you, e raised to minus input domain times output domain. Domain is x, right, over here, and output domain again is x, and f of x dx, and this is the inner integral, and we have this outer integral where we have this inverse Laplace transform of g of x when we expand, say, the left hand side, the right hand side, dx. Now notice there's a problem here clearly, because two integrals with dx, it's like saying integral from 0 to infinity, integral from 0 to infinity, whatever we have inside, dx. Okay, this is a really bad abuse of mathematical notation. This is abuse of notation basically. And another problem is we are losing that parameter of Laplace transform, because now we have e raised to negative x squared here, which is basically the Gaussian function. So Gaussian functions times two functions of x and then integrated with respect to x two times. This is abuse of notation. This is really bad, and we need to rectify this by having a dummy variable. We need a dummy variable, and I'll explain what a dummy variable will do in this context. So instead of writing this integral like this, what I would like to do is, well, first write the outer integral from 0 to infinity of, we have a dx, and inside we'll have integral from 0 to infinity naturally of e raised to minus t times x times f of t times inverse Laplace transform of g of x. Wait, I'm running out of space. So what we have here roughly is basically the inner integral is on dt, and the outer integral, like we had originally, is on dx, and this I'll call our right hand side, and notice that t, in our case t, is this dummy variable that I was talking about. Now what a dummy variable does is, since we can't have x, we assume that the initial starting input domain was t, and that's why we want to end up in x, so e will be raised to t times x with a negative sign, because t was the starting domain and x is the ending domain. And this x will play an important role later on in the next step. You'll see why. So t is our dummy variable. It doesn't mean anything much. It's basically, uh, it doesn't matter. It's like saying that in definite integrals, it doesn't matter what variable you have as long as the structure of the integrand remains the same and the upper and lower bounds. So same thing here. The basic structure of the Laplace transform of f of t is conserved, right? So now I'm going to assume uniform convergence, and I do that so that I can interchange this integral. So I'll have a dx dt instead of a dt dx. And since integrals are from 0 to infinity, it doesn't matter over here. We have e raised to negative tx times f of t times the inverse Laplace transform of g of x dx dt. So all the terms that don't depend on x can be taken outside, can be thrown outside. So outside the first integral, the only term that doesn't depend on x is f of t. That's the entire purpose of having an x here, so that this doesn't get thrown out like the f of t. And because now we can write this as e raised to negative tx times the inverse Laplace transform of g of x dx dt. And now notice what this thing is. That's just the Laplace transform of this inverse Laplace transform, right, by definition. But the output domain now is t, because input domain x has already been taken care of here. That was the purpose of having e raised to negative x, basically preserving the x in the power of e. So now we have integral from 0 to infinity of f of t, and the inner integral is the Laplace transform of the inverse Laplace transform of g of x with respect to t, because the output is now t dt. So by definition, the Laplace and the inverse Laplace transform are going to cancel out, and we have integral from 0 to infinity of f of t times, we'll have g, but it's now a function of t because Laplace transform with respect to t dt. And then again, it doesn't matter what variable we have, we can just change our x or t to x. This means we have integral from 0 to infinity of f of x times g of x dx, which is basically what our left hand side was equal to, and hence proved. So now facts worth noting are, we originally need to start with an integral from 0 to infinity, otherwise we wouldn't have ended up with a Laplace transform when we interchanged the integrals, because if this integral wasn't from 0 to infinity, or was say from 1 to 2, then this would not be a Laplace transform by definition. So it's important to have this so that we can write this as not changing the upper and lower bounds. And one more thing worth noting is, you start with x in both cases and you end with x in both cases, because again we can just change the variables of a definite integral like this. So these are points worth noting when you're using this property, and you'll see in a while why this is a really powerful property. Okay, so once we know the property, let's apply this to our original problem, which was integral from 0 to infinity of 3 times e raised to negative 2x minus 2 times e raised to negative 3x minus 1 divided by 6x squared dx. And now choosing which function to take the Laplace transform of and which function to take the inverse Laplace transform of is more like selecting your d and I or u and dv in integration by parts, and that comes with practice. So trust me when I say that this numerator in our case should be our Laplace transform function and this denominator should be our inverse Laplace transform function. So our integral can be written as integral from 0 to infinity of the Laplace transform of 3 times e raised to negative 2x minus 2 times e raised to negative 3x minus 1 times the inverse Laplace transform of 1 over 6x squared. All of that is integrated with respect to x. Now it's actually time to find the Laplace transform of this part that we defined, and also the inverse Laplace transform of this. So for the Laplace transform now again, we can use the definition integral from 0 to infinity of e raised to minus st times e raised to, let x be t for this case, for the general case, minus some constant a times t dt. This is nothing but integral from 0 to infinity of e raised to negative t times s plus a dt. This is nothing but negative 1 over s plus a times e raised to negative t times s plus a evaluated from 0 to infinity, and then finally this just becomes 1 over s plus a. So if you have like a negative constant, in this case negative 2, this will just be the final variable plus that constant. And in general this is called the shifting theorem, because if you have say some function f of t, you take the Laplace transform of it, f of t, if you have a function multiplied f of t multiplied with some exponential factor like this, say e raised to negative bt in this case dt, this is nothing but the Laplace transform of basically f of t, and then you shift it. So say if you end up with f of s, you have to shift it by b unit, so s plus b. So, and you can show this that if you have the integral from 0 to infinity of e raised to minus st, basically Laplace transform say sine of t times this exponential factor of e raised to negative bt dt. Well, the Laplace transform of sine is basically 1 over 1 plus s squared, but because we have the shifting factor, this becomes 1 over 1 plus s plus b the whole thing squared. So instead of s you just substitute s plus b, and if you have a positive bt, this will be s minus b. So we can use this property to find the Laplace transform of whatever it is we need it to find. So let's find the Laplace transform of this thing. So the Laplace transform of 3 times e raised to negative 2x minus 2 times e raised to negative 3x minus 1 can basically be split up into the Laplace transform of 3 times e raised to negative 2x minus Laplace transform of 2 times e raised to negative 3x minus the Laplace transform of just this one that we have. And basically the 3 can be taken out and this will just be 3 over, but notice that even after taking the Laplace transform we need to end up in x, right? Because if you remember those conditions that I had talked about of applying this, we need to start and end in the same variable. So 3 divided by, instead of s we'll have an x plus 2 minus 2 over x plus 3 minus Laplace transform of 1 is just 1 over s, but in our case s is x, so x. So there we have found the Laplace transform that we needed to find. Now it's actually time to find the Laplace transform of this. So for this I urge you to look at the Laplace transform of, say, t to n. You have the integral from 0 to infinity of e raised to minus st times t to the n dt. Now if you want to make a quick substitution, say w equals st, you can do that. Upper and lower bounds remain the same. You have e raised to negative w times t is w over s, so w over s to the nth power, and then dt is nothing but dw over s, so dw over s. Finally we have s to the negative n plus 1 power times integral from 0 to infinity of e raised to negative w times w to the n dw. Notice this is just the gamma of n plus 1. So this will become gamma of n plus 1 divided by s to the n plus 1th power. That's nothing but the Laplace transform of t to an arbitrary n power. So now let's, on rearranging certain terms, first we need to, since we needed to find the inverse Laplace transform of 1 over x squared, so we need power of s to be 2. So if we let n equal 1, we have the Laplace transform of just a single t to be the gamma of 2 divided by s squared. So if we say we have taking the gamma of 2 on that side, Laplace transform of t divided by gamma of 2 is nothing but 1 over s squared. Now take the inverse Laplace transform, because the gamma of 2 is just 1 factorial, which is, well, 1. So this will just become t now over gamma of 2 is inverse Laplace transform of 1 over s squared. So the inverse Laplace transform of 1 over s squared, in our case the s was x, is nothing but t over gamma of t, but since we need to start and end in x, this is nothing but x over gamma of 2. So we can make that substitution in here with the factor of 1 over 6. So the inverse Laplace transform of whatever we needed to find is just 1 over 6 because of this original factor times x over gamma of 2, and gamma of 2 is 1 factorial, which is 1, so we just end up with x over 6. So we can substitute all of this in our original integral. So our original integral I just becomes integral from 0 to infinity of, well, for the Laplace transform we have these things: 3 over x plus 2 minus 2 over x plus 3 minus 1 over x times the inverse Laplace transform, which is basically x over 6. And don't forget the dx that we have here initially. We can take the 1 over 6 outside. We have integral from 0 to infinity of 3x over x plus 2 minus 2x over x plus 3 minus x over x, all integrated with respect to x. So I want to make the numerator a multiple of the denominator so that we can cancel out some common terms. So 3 times the denominator is basically 3x plus 6. We have the 3x, we just need to add and subtract the 6. So 3x plus 6 over x plus 2, and then we subtract the 6 over x plus 2, and then again we can do the same here. So 2 times the denominator is 2x plus 6. We have the 2x, so 2x plus 6 divided by, say, x plus 3, or let me just take this factor inside. when we have a negative for the inside terms. So I took the minus inside, so minus 6, but then we have to add 6 because we did not originally have a 6. We can't just pop it in when we like. Fair enough. And this is just minus 1, and all of this is integrated with respect to x. So this becomes 1 over 6 times the integral from 0 to infinity of, this goes with the denominator 3 times, so we just have 3 minus 6 over x plus 2. This goes with the denominator again negative 2 times, so negative 2 plus 6 over x plus 3 minus 1. Dx. So notice 3 minus 2 is 1, and this minus 1 will cancel everything off to 0. So we just have 1 over 6 times the integral from 0 to infinity of 6 over x plus 3 minus 6 over x plus 2 dx. So this just becomes 1 over 6 times, integrating this is really easy, 6 times the natural log of absolute value of x plus 3 minus 6 times the natural log of absolute value of x plus 2, all of which is evaluated from 0 to infinity. So we can cancel out the 6's out. We can write this as natural log of x plus 3 divided by x plus 2 evaluated from 0 to infinity. So for the infinity case, we can take the limit as x goes to infinity of the natural log of x plus 3 divided by x plus 2 minus the natural log of, well, when you plug in 0, this will just be 3 over 2. So we can take the limit inside the natural log. We have the limit as x tends to infinity. I can write this as 1 plus 3 over x divided by 1 plus 2 over x, right? I'm just dividing by x, and then since they are a ratio, the final denominator x will cancel out in both numerator and denominator. So we have natural log of 3 over 2 on this side. So in the limit as x tends to infinity, this will go to 0, this will go to 0. So we just have natural log of 1 over 1. So natural log of 1 minus natural log of 3 over 2. Natural log of 1 is 0. So I is nothing but negative natural log of 3 over 2, which if you want to suck up the negative, you can flip the inner argument, will be natural log of 2 over 3. That's basically your final answer for that integral. It's really fascinating that we get a number which is negative in this case. In most integrals it was positive, but in this case it's negative 0.405465. So it's a pretty nice result. We got a natural log, not any pi or some other weird stuff. Okay, so this is basically the power of the new Laplace transform property that we learned. I hope you really liked it and you learned something about it. But here's a catch, there is actually a shortcut method to calculate this, because mathematicians like shortcuts. So there's another general theorem, a general property of Laplace transforms to deal with integrals of the form, say, of some function of t divided by t to the n dt, and provided that this obviously converges, is basically equal to the limit as s tends to 0 of integral from s to infinity of 1 over n minus 1 factorial times the Laplace transform of the n minus 1th derivative of f of t with respect to s, because Laplace transform of t we can assume will give a function of s. So we can apply this property and notice that our denominator, in our denominator, n is equal to 2, and our f of t, you can say, is, you can change x to t, 3 times e raised to negative 2t minus 2 times e raised to negative 3t minus 1. And since n is 2, it's derivative of n minus term, so it's the first derivative of this f of t. We need to take the first derivative of f of t. So first derivative of f of t, this is 1, is minus 6 times e raised to negative 2t plus 6 times e raised to negative 3t, and this will just go to 0. And then they're telling us to take the Laplace transform of this. So our integral I is nothing but limit as s tends to 0, is from integral from s to infinity of 1 over 2 minus 1 is 1 factorial times the Laplace transform of basically the first derivative, which we just calculated to be minus 6 times e raised to negative 2 plus 6 times e raised to negative 3t, and integration with respect to s. But we also have this 1 over 6 factor. So now this is just the limit as s tends to infinity of integral from s to infinity, limit as s tends to 0, sorry. 1 factorial is 1, we just have 1 over 6 times the Laplace transform of this is easy. We can pull out this factor of 6. This is nothing but, I'm just doing it very quickly now, minus 1 over s plus 2 plus 1 over s plus 3, basically shifting theorem again, ds. We can take the limit and this will become integral from 0 to infinity of 6 over 6 is 1, so that goes away. 1 over s plus 3 minus 1 over s plus 2 ds, and antiderivative of this is natural log of s plus 3 minus natural log of s plus 2 evaluated from 0 to infinity. If we do that, we obtain a similar expression that we did before, evaluated from 0 to infinity. This will be the, well, for the infinity case, this will just be the natural log of 1, so it will go to 0 over here, minus natural log of, when we plug in 0 for s, we have 3 over 2. Taking the negative in, we can flip the inner argument to be natural log of 2 over 3. So that was the shortcut to calculate this integral using this general property, and I'm going to prove this in probably one of my future videos. So stay tuned for that. Meanwhile, I think that's enough for today. So please like, share and subscribe to my channel. Recommend me to your friends. I'm making more and more content. I want more viewers. I want more subscribers naturally. Subscribing to me is, and sharing my videos is one way you support me to make interesting math videos. You can follow me on Instagram. I have this username gamma_digamma. Meanwhile, stay home, stay safe, have a great day. Peace out.